Question 2 says that if two equal chords of a circle intersect within the circle, prove that the segments of one chord are equal to the corresponding segments of the other chord. So let's draw a figure so that we can understand this problem better. So here's a circle that we will use for this problem. And now let's draw two chords in this circle that have equal lengths and that are intersecting. So let's say that one of the chords is this chord, and let's take another chord like this, and these two are equal chords. So let's name them now. A, B is one chord and C, D is the second chord, and A, B and C, D are equal. And let's take this point of intersection as X. Okay, so we have to basically show that the segments of one chord are equal to the corresponding segments of the other chord. So the segments of AB are AX and BX. The segments of CD are CX and DX. So we have to prove that AX and CX are equal, and we have to prove that BX and DX are equal. Alright. Okay, so to prove the required result, we are going to make use of the fact that equal chords of a circle are equidistant from the center. So I'm going to write this result that we'll use directly. Equal chords of a circle are equidistant from the center. They are at the same distance from the center. So this is what we are going to use. AB and CD are two equal chords, so they should be at the same distance from the center O. So let's drop perpendiculars from O to the two chords. So here's one perpendicular to AB, and here's the second perpendicular to CD, and these two perpendiculars should be equal because AB and CD are equidistant from the center. Let's also join O to this point of intersection X, and let's label the feet of the perpendiculars as M and N. So what we are going to do now is we are going to compare the triangles OMX and ONX. So I'm going to highlight these two triangles for you. So we will compare OMX, this triangle, with ONX. ONX is this triangle, and we will show that these two triangles are congruent. Okay, so let's write this. So in triangles OMX and ONX, what are the parts which are corresponding parts which are equal? So we saw that OM and ON are equal because of this equidistant thing. Both the chords are equidistant from the center. We also have this hypotenuse OX common to both the triangles. So OX and OX, this is a common side. And I said hypotenuse because both of these triangles are right angled, because OM is perpendicular to AB and ON is perpendicular to CD. So angle OMX is equal to angle ONX, and both of these are equal to 90 degrees. So we have two right angled triangles in which one pair of sides and the hypotenuses are equal. So we can apply the RHS congruence criterion and claim that the two triangles are congruent. So triangle OMX is congruent to triangle ONX by the RHS congruence criterion. And because of this congruence condition, we can now say that this side MX in triangle OMX and NX in triangle ONX, these two sides are equal by CPCT. So let me write it as XM. So XM is equal to XN, and this is by CPCT. Now I'm going to show you how we will use this fact that XM is equal to XN. We dropped OM and ON as perpendiculars to AB and CD, and we have this result from circles that if you drop a perpendicular from a center to any chord, then the perpendicular bisects the chord. So this means that M, this point, will be the midpoint of chord AB, and N will be the midpoint of chord CD. So we can write AM will be equal to BM and CN will be equal to DN. So AM and BM will be equal to half of AB and CN and DN will be equal to half of CD. But we also know that AB and CD are equal, so their halves will also be equal. In particular, AM and CN will be equal. So let's write this here, AM and CN will be equal. Now I'm going to make use of this fact to prove that AX and CX will be equal. So AM is this segment joining A to M, and CN is the segment joining C to N. So if you observe these two segments carefully, AM is made up of two parts. It has AX and XM, and CN has CX and XN. And because XM and XN are equal, AX and CX must also be equal. So let's write this fact. So AM is equal to CN and XM is equal to XN. So if we subtract these two equations, on the left hand side we will get AM minus XM, and you can see from the figure that AM minus XM will be AX. So this will be AX, and on the right side we will have CN minus XN, and CN minus XN will be CX. So AN is equal to AX is equal to CX, and similarly we can prove that BX is equal to DX, and to do that I will make use of the fact that BM is equal to DM. So this part BM and this part DN, these two are equal because they are halves of their respective chords and the chords are equal. So BM is equal to DN, and now to BM if we add MX and to DN if we add NX, we will get BX and DX. So BM is equal to DN and XM, or let's write this as MX. MX is equal to NX, and now if we add them we will get BM plus MX on the left side, which is BX, and on the right side we will get DN plus NX, which is DX. So once again let me summarize what we did. To show that AX, this segment, and CX, this segment, these two are equal, we took AM and CN, they are equal. From the respective sides we subtracted XM and XN because these two are equal. We showed this by CPCT, and then we just subtracted. So here we subtracted the two equations and we got AX is equal to CX. For the other pair of segments, BX and DX, so BX was this segment BX and DX was this segment joining D and X. We made use of the fact that BM is equal to DN because they are halves of the respective chords and the chords are equal, and MX is equal to NX, again this same result we used it again, and then we added these two equations to get BX is equal to DX. So this proves that the corresponding segments of the two chords are equal, and that completes question number 2.
To learn more about how QMath can help you crack school and board exams, explore QMath Leap, a live online classroom program run by highly experienced and committed teachers.